walks can be thought of as random walks in which the head of the walk experiences an infinitely repulsive potential at points already occupied by the walk and zero potential at points that are unoccupied by the walk. We can calculate the mean square end-to-end distance and the mean square radius of gyration of such walks in two different ways. We can use the reciprocal of the cardinality of set of n-step self-avoiding walks as the probability of the walk, and this is called the uniform probability. Secondly, we can calculate the probability by, at each stage, the head of the walk takes the reciprocal of the number of vacant sites as the probability, and then takes the product of all these probabilities. Here we assume that this number of vacant sites is not zero, so it is a conditional probability that the walk is not trapped. These ideas were enunciated in detail in the physics literature about 30 years ago, and in a recent paper by myself, which I show over here. The same idea was exploited by Dr. Nisha Satheesh in her PhD thesis, but using more realistic lattices and more realistic potentials. She used the tetrahedral lattice or the diamond lattice and Lennard-Jones and Kihara potentials. And what she observed was, when she looked at uniform walks, as expected, there was a collapse in the polymer dimensions. However, when she used the growing self-avoiding walk, which I just mentioned earlier, she observed no collapse. This means that as a growing polymer chain, as it grows in the form of a rigid coil and collapses after the reaction is complete.